Well, that's good. Well, Carl, what normally happens is we have a bit of a chat first, wait for a few more people to join, and then we crack on.
Cool.
I've got my things on my list to talk about tonight, hopefully, which is latitude and longitude. We want to talk about the because I think I have seen it in one of the exams before now about decimalising the latitude and longitude. Have you read about that?
No, I've not read it.
Just came in with
Yes, it cropped up in just a second. Yes, it cropped up in one of the exams. It would appear in some industries they rather than just use degrees, minutes, and seconds, they then decimalize it. So
it is in the NAV book?
Yes, I think it is. Yes.
We come across it 2020.
Yes.
Yeah.
That's right, because they were asking to plot a position, and it didn't make any sense. We suddenly realised that the numbers were going greater than 60 minutes. So it's like 1 degree, 65 minutes. Thinking, well, that's not right. It can't be, can it? It can only be 60 minutes. And then it moves on, doesn't it? It becomes the next degree and so forth. So anyway, yes, there was a bit of that. So I wanted to oh, man, let's see one. No, there we go. I'll send that to him. Anyway, so that was on my list, and time zones as well. Especially as recently, I did a trip to France, but we're playing with 3 different times now, and it gets a bit of a headache if you don't write it all down, because you suddenly have Greenwich Mean Time, don't you? Universal Time Coordinated, then you've got our British Summertime, then you've got French Summertime, and depending on what it is you're trying to organise, depends on which one you're looking at. So yeah, it's all good fun. It's managed.
So I can just work it out. Yeah.
But it's a pain because
It's a pain, yeah.
it says, "Oh right, well, what time are we going to eat dinner?" And you're like,
Don't.
6 o'clock French
I
time.
give it to you in universal time.
I mean, it's 6 o'clock French time. That's 5 o'clock our time. It's 4 o'clock. Universal Time Coordinated. Yeah, but now you've got to plan your flight and bump backwards and forwards in all this. Anyway, it gets a bit of a headache sometimes. Then we're going to hopefully talk a little bit about the compass. What a marvelous bit of equipment, but it does have a few errors, or it can suffer from errors. Units of distance, of course, because they're a little bit jumbled up in aviation, aren't they? We have the combination of metric and imperial, basically. And then choice of chart, because we always just end up grabbing a quarter mil, but not necessarily. And then dead reckoning is that bit where you start to calculate for drift. And if we get onto it, a bit of radio navigation as well. Anyway, there we are. There's my list. Right. So one of the things I want to do, if I can manage this.
I can already share.
Can you?
Yeah. I mean, I will just give it a go.
Give it a go, just to double check. So James is going to use his iPad to share certain things that I'd normally be sharing, possibly a bit of Sky Demon, or if he needs to draw something on a whiteboard. But we'll see if that is going to...
Closing my suspicious tabs.
Yeah, don't share any of that, will you?
That was a joke, by the way. This is being recorded.
So you see.
I have no idea where the recording's going either.
Okay, so I'm now broadcasting.
Yes, you are indeed.
Can everyone see?
I can, yeah, that's looking good.
No, that's not what I wanted to do.
Oh.
I wanted you to be able to see that.
Hey.
Oh, there you go. It is working.
Good.
There is quite a delay on it, isn't there?
It's interesting. You can share that without actually having the permission on it already.
Yeah,
I
there's
don't
a
know how it
lot
works.
of
Oh, well.
delay there.
You're going to mirror it on the show.
Is everybody still there at the moment?
Yeah, still here.
Okay,
Yes,
that's
still
good.
here.
Good, thank you. So we're just seeing if we can get over our sort of technical difficulties here. Yeah, it's there.
All right.
It's just okay. Good.
Okay.
That works well.
Off for now.
Okay, so oops, can't see everybody. Somebody that maybe not so sure. So if you know the answer, obviously just hang back for a second. What is latitude and longitude? Screen make sure of that. Anybody not entirely sure? Blimey, everybody knows what it is. This is really good. Okay, right, we'll just move on then, shall we? All right, so where did it derive from?
I don't know.
Just there.
Not where it was.
It just happened.
Yeah.
It's there, yeah. Maritime, wasn't it?
Was it from nautical, from seafaring?
Yes, of course, because generally speaking, we were in boats and etc. We weren't before we were in aircraft. This is why it ends up being, you sometimes see that term aeronautical, because there is a lot of similarities in the way we do things. So one of the problems of or one of where latitude and longitude sort of stemmed from was, how do you, when we finally realised that the world was pretty much round, how do you flatten that and put it onto a chart? How do you measure distance across it? How do you even divide it up? You know, you can't just cover it in squares and say, oh, well, look, we'll just put squares on it and we'll say each one is 1 and divide that down by 10, because it just doesn't work, because it's not too bad, maybe, depending on how you can do it near the equator, for instance. But as you move up, and you can see, you won't be able to see it online, but on here, there are something that looks vaguely like a square, but as it moves up, they get squashed into a point right at the pole, at the North and the South Pole. So, you know, I can only imagine that they've devised a way of, well, why don't we clearly can't easily draw straight lines on it. Well, yes, we can, but no, we can't. You see, we can draw lines straight from up to down, i.e. North Pole to South Pole, and we can maybe draw one around the centre. But as soon as we try and draw other lines around here, actually, they're not very straight. Certainly not on here. They've got a bend to them. And one of the best examples of this is if you have a look at something like flight radar and what the planes going from, say, the UK to America, they appear to be flying a bit of a curve across the globe, across the world, like this. But as far as the plane's concerned, it's in a dead straight line. It's only because of the distortion of how our phone has flattened out the world that it appears they're flying a curve. Okay. So some bright spark, I can't remember the name of them now, said, well, why don't we take the centre of the world, right at the centre, and if we divide it, because it is a circle, if you just look at it two-dimensional, a circle is 360 degrees. So why don't we just divide it into 360 degrees, first of all? That would work, wouldn't it? Okay, so that's good. So at least we've got now a unit we could work with. But what does 1 degree equal?
60
6
nautical
minutes.
miles.
It does, but what came first, the nautical mile or the degree?
The degree.
It did, as far as I'm aware of. Always happy for anybody to look it up and correct me, no problems at all. But yes, so if you divide the world 360 degree from the centre, of course, 1 degree will measure a certain distance across the surface. That we could, if we break that down into minutes, maybe, that'd work, wouldn't it? So we could have 60 minutes in 1 degree. So therefore, if you divide that degree by 60, you get 1, and we'll call that a nautical mile. Hey, that's a very short version of it, by the way, but that's roughly how it works. So we therefore know that if we travel over the Earth's surface at 60 nautical miles an hour, A, in 1 hour we'll have done 60 nautical miles, but B, we'll have travelled
1 degree.
1 degree of arc. Yeah. And that works. Brilliant. But can we do that both, if you will, vertical and horizontal? Oops.
Yes.
Yes, we can.
Because it's a sphere. So.
It is, more or less. I know it's not quite,
Yeah.
but it's good enough for now. It's absolutely fine for now, isn't it? And that would kind of work, wouldn't it? So let's just concentrate on the up and down bit for a minute. Well, somebody decided clearly that this is the top and that's the bottom, i.e. North Pole, South Pole, isn't it? I mean, who knows? It could be the other way around, but there is a top and a bottom, north and south. And so that maybe naturally splits it in half, doesn't it? And we've got the equator. So therefore, there'd be no need to sort of do 1, 2, 3, 4, 5 and go all the way around to 360. We could easily just halve the 360 and we've got 180. Would that work?
No.
Because
Because you've already got your 360 going round.
yeah, we still got
So
to.
you don't want 360 going the other way.
Yeah,
as
that's
well.
right. We don't want to confuse it, do we?
Yeah.
So what do we do then, Tony?
You go 90, 90.
Yeah,
So it's 180.
because we can easily split it in north and south, can't we? Brilliant. And that works because it doesn't matter where you are you could be 1 degree north, and it's always going to follow the same line around the world, isn't it?
Yeah.
Because we know that these circles, if you will, these rings get smaller and smaller. But for now, vertically, it doesn't matter particularly. It's still just 1 degree until, as you rightly say, you get up the top there, and it's going to be
No. 1 degree.
down the equator. Down the equator, it's going to be
0.
0. So the 0 line's the equator. So you got up to 90 north and then 90 south, haven't you?
Yep.
Brilliant. So that's the vertical bit sorted, and they're nice even increments all the way around, as long as you go directly up and down, north south, isn't it? So far, so good.
Yeah, so far. Yeah.
Good. All right. So looking down from above, well, there's no kind of where does east and west begin, or where's the beginning, where's the end?
England.
Yes. So, somebody, I don't know who, let's just say, yes, indeed. He said, well, I think we should,
Centre of the universe is
England is
here.
clearly the centre of everything. So let's just start here, shall we? Because it's the most important thing. Yes, is where I am. I live in Greenwich. Yes, so Greenwich became the start, called not just the meridian, but the prime meridian. Yeah. And it's all going to revolve from there. That works because if you go one way, you're traveling east. Good. So we could say that's an east by a certain amount. If you go the other way, west. But of course, therefore, that does mean you get to the other side of the world and it jumps, doesn't it? So you go east, 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 and suddenly hops over to west. So if we start with 0 here on the prime meridian, that's it, and work our way around, of course, we're going to say 1, 2, 3, 4 degrees of arc. But it only works at the equator, really, doesn't it? So 1, 2, 3, 4, 5, right the way around to 180 east, and then 180 west. But you can hop the other side, can't you? From 180 east to 180 west. You jump across. Everybody okay with that so far?
Yeah.
But from that, and of course these lines can also be divided by 60, but at least from that you can now plot somewhere on the world, can't you? You can find vertically from north to south the degrees, and you can split that down into minutes, and then you can split the minutes down into seconds of time by measuring how fast you're flying. So we could fly for 60 minutes, 60 seconds, 1 hour. Oh jeez. Hang on a minute. Let's just go back a second.
He is awful ways now.
You could travel for let's do 2 hours, so 2 degree of arc, for 30 minutes, half a degree of arc, and then you could do 60 seconds, so 1/60th of a degree of arc, and potentially you could even split that down further, couldn't you, if you really, really wanted to? But at least you've measured vertically where you are. And then you can do the left and right by the east and west by once again. All you've got to remember is that the east and west arcs do get smaller as you go up, so they're not the same measurement. So one of them down here may well be 60 nautical miles, but up there it certainly isn't. In fact, at the North Pole, you take one step and you've travelled several arcs, haven't you? Or several ways around, several longitudes. So imagine that, a quick dance around the North Pole.
So you can circumnavigate the world very quickly.
Yeah, absolutely. In a couple of steps, you've just done almost like a rumba. That's it. You've gone around the world, circumnavigated. Yep. But that's at least, like I say, we've got some sort of grid system on the Earth's surface now that we can work with. Great. So how does that kind of translate into a chart? Because we can't take that into the helicopter and go flying with it. That's just not going to work as far as I'm concerned. Because the scale's too big, isn't it? Small, big, big. So how does that turn into that? So I'm just pointing at, how does the globe turn into this, the chart?
By projection or by flattening the Earth?
Hey, hello, Sophie.
Hello.
Yeah, you see, to get rid of distortion, what we could do is if this was made of paper, we could get some scissors and pretty much cut every single line that goes up. In fact, we could cut multiple lines. In fact, literally every single tiny little degree, and flatten it out. Yeah, it would be a bit tricky because the chart would have lots of gaps in it and trying to hop over the gap as you navigate along. But it'd get rid of distortion, wouldn't it? Or would it?
No.
It still wouldn't work because up here these would be spread out wide. So the distance is no good. So you'd have to imagine the gap. You'd have to eliminate the gap. It'd be a nightmare, wouldn't it? Utter nightmare. So that doesn't work. You could maybe put a few cuts in it and sort of semi-flatten it. You're going to get a few ripples and bulges in it here and there, aren't you? But won't have quite so many gaps. But that still doesn't really work. But that's more or less what they do on the charts, isn't it?
Yeah.
To a degree. So you say we're going to try and maybe project an image of the area you're looking at. Now, of course, we don't want a chart that covers the entire world. Certainly not for navigation at the speeds we're flying at, because it's just never going to work, is it? So you could take just a very small little area of the UK, understanding that because it's a curve, if you flatten it, it's going to have some distortion. But there might be a certain way that we can project it and minimize or average out the distortion and keep it to a fairly small amount. And that's what we do. Well, that's what the cartographers do, don't they? But how does that look on a chart, that distortion? Have you noticed it before?
I'm just trying to figure out
The latitude lines aren't straight.
Yeah, that's right.
Curve.
So
Quite like
oops, let me flick it around. Where's my... Yeah, when we look at some of our charts, and of course it's actually more prominent on a half mil chart and even more on a 1 mil chart. So this is only a quarter mil chart. But even on here, you start to notice, look, somebody's drawn these lines wrong. These are not straight. They're not parallel to the edge of the chart. This one leans in a little bit this way to the left. But if I go over this side, oh, actually, that's not too bad. That's fairly straight, but clearly there's already that slight distortion there visible. And indeed, if you got a set square out and tried to put it on here, it wouldn't be perfect. They're just not quite right. And we can start to see that, look, that line goes up there, whereas that one's a little bit more straight. So the distance across here is actually slightly less than the distance across here. But it's only slight. It's not enough. Yeah, it's only slight. But indeed, if we actually got James's ruler and tried to draw a point, maybe, I don't know, from the tip of Margate right the way across to somewhere over near Cardiff or something along those lines, we would draw a perfect straight line on the chart, figuring we're going to go fly a straight line. But it wouldn't actually be straight. It'd be a slight curve actually to the left when we went and flew it, because we'd have to draw the curve slightly like this, known as a room line?
Room line.
Yeah, that's it, a room line. So a room line on our charts usually looks wrong because it's got a slight curve, but however, actually it's a dead straight line.
Called that a rum line.
Oh, room line. Yeah, that's fine. Yeah, same thing.
Get it?
RH. Oh, rum line. Yeah, very good. Oh dear.
I apologise.
But over the distances we're flying, it just, we're unlikely to fly from there right the way across to there without doing a single turn. We're probably going to have to avoid something. So our distances get shorter and the distortion is even less, and it's just unnoticeable. Okay. So what, Ross?
yes.
Yeah.
Oh, yes. Here we go. Right, go on.
So we've got some numbers on here. Look, what's that? What's
1
that?
degree, 30 minutes.
Yeah, 1 degree
East.
what? Which means it's
1 minute, 1 hour, 30 minutes east.
yes, from the equator. If you're measuring it on the equator.
Yeah.
Yes, if you remember, once again, if we went right up north somewhere and went from the 0 line to there, it would not take 1 hour and 30 minutes at 60 nautical miles an hour. But it would at the equator.
Would. Right.
So
yes.
that's only those lines, the separation or distance between those lines is only actually accurate down the equator, isn't it? As far as that measurement's concerned, if we were going to try and time it via speed.
Right.
Yeah? However, going up and down is all right,
Yes.
doesn't it? Because you've got, for instance, up here, you've got 52
North,
to.
52, 30 minutes more.
So if you flew at 60 nautical miles an hour along that edge of that chart, how long would that take?
Oh, that will take 30 minutes
Yeah.
from there to there.
That's right. So that measurement there should be the same as down here and here and here and here. So that all makes sense.
Yes.
So up and down, it makes perfect sense as far as if you're going to try and measure like, but left and right, it doesn't. That took a while to fathom them out.
Hmm.
But once again, we've got this grid system now, haven't we? That we can identify a place, we can find a latitude and longitude and pinpoint it. Any questions there so far? Good. So, if Ross, you were, sorry, Ross, if you were, let's just say 1 degree 30 south,
Okay.
and you flew to 1 degree 30 north at 60 nautical miles an hour, how long would that take?
That should take 2 hours, shouldn't it?
Any others?
I'm 30, so
3 hours.
3 hours. Yes, because of course, don't forget you're going to be flying from south. First, we've got to do 1.5 hours to do the 1 degree 30 minutes.
Yeah.
1 degree 60 seconds. That's 60 minutes, isn't it? So you've got 90 minutes north just to do the other 1 minute, 1 hour 30 or 1 degree 30. Yes, so 3 hours in total. And that's a question that quite often crops up in the exam. And if you don't spot the S for the south, you'll get it wrong because you'll think it's just north to north. Yeah, and it's not. It's from south the equator to north the equator. So you've got to tick down first of all, haven't you, to 0, and then go back up again the other side. Good. Lucky for us, we're just north the equator, so it's all fairly easy, isn't it? Is there anything else I wanted to say about that for the moment? No, I think that's fairly straightforward. Right. So we got, this is just slightly now out of date, this is a 2022 chart, but whilst we're on, I might as well quickly mention, oh, I can't work how you do that. Somebody wants to join and I'm still on that screen. Okay. Yes, so James is just mentioning it now, of course, when we navigate on these charts, what do we use to determine if we're going in the right direction apart from features?
Compass.
Yeah, we use the compass, don't we, Tony?
Yeah.
Good.
My thanks.
Okay, and is the compass good? Is it bad? Is it all right? Is it?
It's all right, isn't it?
Yes, all right. What's all right about it?
It points in a northerly direction when you want it to, and all the other directions depending on which way you're facing.
Yeah, it does sometimes, doesn't it?
Hopefully, most of the
Doesn't need
time.
batteries.
Yeah.
It's pretty good, isn't it?
Yeah, absolutely right.
Yep.
So
And works anywhere in the world?
It works better here than it does.
Ah, yes, that's
This.
right. So it works okay.
Yeah.
In some parts of the world, it works really, really well. In other parts, yeah, it's not great, is it? No. So we have got that to deal with,
Yeah.
haven't we? So, and of course, the compass points to
Magnetic.
good,
Yeah.
magnetic north. So is it making everybody seasick if I swing the phone round?
Yes.
Yeah. At home, they've all got a bit green like this, so I keep swinging it around. Yes, so it points to magnetic north, whereas the charts point to.
True.
They do. Oh, bugger. So, what are we going to do about that?
Blue lines, which I can't remember what they're called, that tell you the deviation of the magnetic line.
Yeah, good. That'll.
It's minimalistic here, but I think where Sophie is, it's huge.
Yeah. So, what's your magnetic variation, Sophie, again in Montreal?
-14 east.
14. Yeah, 14. And we
14,
whinge.
yeah.
And we used to whinge when Az was about 1.5. She has to deal with 14 degrees, and that's significant, isn't it? Az at the moment is so small; it's just gone to east, isn't it?
Yeah, it's gone to east.
Yeah, as is our deviation or
45
variation
degrees
is
east,
so
isn't it?
small. It's just next to nothing for where we are.
Here,
But we need to understand that there is a difference because depending on where you are in the country / in the world, yeah, your compass, whilst it's a great bit of kit and it doesn't require batteries, first of all, might have quite a bit of an error because it's looking at the magnetic pole, but our chart isn't. So we need to know that, don't we?
Of course.
Or you could be so far up the world or down the world, if you like, close to the North or South Pole, and because of the magnetic forces dipping into the North Pole, the compass likes to point down, so it follows those lines, doesn't it? So what's the problem with, who should we pick on next? What's the problem?
Hello, Ross.
What's
Tony's got it.
Not the pizza, is it?
got to be as smooth as I can. Oh, I know. We could let's get James on to sharing. Do you want to do a bit of drawing on a whiteboard screen?
I can, yeah. I'm getting my pen.
So James, in a minute, I'm going to get him to draw, because this is going to be really hard for me to do it on my phone. Get him to draw those lines of magnetism around the world. But I think most people kind of know they come out, from the magnetic north, not quite the centre. They come out, they go round. They're fairly parallel to the Earth's surface around the equator, but then they start to dip back in again at the other pole. And our compass likes to follow those lines, doesn't it?
Yeah.
So if you're too high up, it starts to dip towards the Earth's surface, and same with the south. So James, if
I
you,
might overtake it.
yes, fine, yes, quite right.
Okay. Right. Can you see a whiteboard?
I can indeed.
Yep. Can you see that?
Yes, we can say hello.
Perfect.
So hopefully James is going to draw a beautiful Earth with all the countries on it and colour it in, and then he's going to draw those
It's already going wrong.
as magnetic fields.
Or can I just ask a question?
Yes, of
And
course.
it's probably a really stupid question, so please don't laugh too loud. But
Okay.
so our charts are updated, aren't we? So you've said the one that you're looking at now is like 2022, so it'll be updated. So why don't they, when they're updating their charts, also update it to take into account what magnetic north would be in that particular area? Say, for example, if I had the up-to-date Montreal map, everything should shift, shouldn't it? So that everybody's looking at the same thing. And the world is looking the same as your compass is. Why don't they just do that?
But do you mean, why don't they just draw the chart with the magnetic variation already applied to it?
Yes.
Well, because if you do that, you're then got to probably just rewrite the LAT LONG on the Earth's surface of the globe, of how we're measuring it, to do it from magnetic north and south. And there's a problem with that it keeps shifting.
But does it shift within a year? Like, how often does it shift?
All the time. It's constant, and it's also not in a uniform manner. It's in a very random manner. If you look up magnetic variation, even just on Wikipedia, it zigzags across. It's heading towards Russia or something at the moment, isn't it?
Russia was stealing it quite well.
Yeah.
I don't know if that's still true.
Okay.
When I first learned about it, it was almost taught that it just kind of circles around every 902 years, but it kind of does. But however, it actually does it in a very uneven fashion.
So within a year, it will shift. So it will go from east to west, and the numbers will be different. Potentially, it could be different.
Depending on where you are in the world, depends on how much that shift is. You can't just simply say, oh, in 1 year it shifts 1 degree. It does depend where you are. Right.
Okay. Understood. Okay.
Yeah. So the charts are updated with that variation on there at that moment of time. I'm certain they put it what it is at the time of producing the chart, not some anticipated 6 months ahead or whatever to try and average out. It's like that's what it is now, right now. Okay, so there we are. James very kindly, he's drawn some magnetic fields on the Earth.
Not very good.
That's all right, it's cool. And the arrows, yeah, the arrows representing the compass, or the bar of the compass that's hiding inside the compass, the very heart of it. And as we can see, the further up the world you go, or indeed down, the more it wants to point to the Earth's surface. But why does that make the compass not so reliable? Just because it points downwards a bit?
Well, because the compass is kind of like flat, and it's.
It is.
How do I describe it? It's kind of like touching itself.
But if we does everybody see James's magnetic fields? We'll just stop showing that for a second, please.
Yep.
Hey man, how you doing? You right?
Do that.
All good, Paul. Thank you. Thank you.
Hopefully you get to see your lovely face again in a second. Hey, there we go. Right. Unfortunately, we picked on poor Ross again. But Ross, if we just took a bar of steel that we sort of stroked with a magnet and turned it into its own magnet and put a bit of string around the middle of it and suspended it, and it sort of hangs quite nicely flat.
Yep, nice and
It
flat.
would-
So
It would point north to south, wouldn't it?
That's where it wants to point to where it's originated from.
Magnetic north, and,
Yeah.
and basically, isn't it? Slash, it lines itself with those. Brilliant. And if you went up a bit further up the world, up from the UK, which is already quite high up, higher than people realise, went up a bit further to Iceland, eventually to Greenland, what would that bar on the end of your piece of string do? Would it still be lovely and flat, or would it be a bit more?
No, you've got the magnetic curve. It's going to be wanting to, like say, point downwards towards the floor.
Yes.
Where it's coming.
But it wouldn't point straight down to the floor unless you got literally to the North Pole. And I'm not even sure it would actually point straight down. But anyway, never done that experiment. I'm not sure if anybody has. But why does that make it inaccurate? You know, if you stood there, I'll tell you what, put a tripod up, hang the string, hang the magnetic bar, let it settle, it would still pretty much point to North Pole, wouldn't it? Magnetic north. So it's not inaccurate, is it? Not like that.
As it dips, is it not arcing?
Yeah, but they're kind of that perfectly. And imagine all the way around the world, everyone is almost perfect going into that. You know, no, going in from south to north, isn't it? Yeah. So going in is, isn't it? I've got to think about that myself.
So it's god, no.
Anyway, we'll skip around that for a second until somebody looks out.
The magnet in the compass.
Yeah, that's right. So what I'm trying to get at is if you could suspend that basically very crude compass we've just made perfectly still, it'd probably be half decent. But in a helicopter, it's not perfectly still, is it?
No.
Jiggling around all over the place. And not only that, it's not only is it jiggling around and subjected to various forces, of course, you're going to probably, at some point, you're going to turn, aren't you?
Yeah.
So what happens to that magnetic bar that's inside there when we turn the aircraft?
No, it's not reliable, so that's why you meant to use your directional indicator when you turn.
Tony sitting very quietly, look. So.
Oh no, I'm fascinated by that.
Right. Well, what happens is that magnetic bar that's sitting inside the compass. I don't think they'll see that, will they?
Magnet, by the way, in the North Pole.
Okay. I need to. Oh well, anyway, I'll have to do it with my hand. Well, sitting that magnetic bar in the helicopter, it points downwards a little bit, and it kind of, if you will, almost makes one end slightly heavy as a way to think of it. And when we roll the aircraft, it swings downwards and it tries to still point down because that's what it wants to do. And you turn the other, and it swings down. It's a very crude way of describing it for now, but you'll get the idea.
Yeah.
That starts to make sense, doesn't it?
Yeah.
Because in a straight line when we fly, generally speaking, the compass settles down reasonably well, doesn't it? But when you turn, it either whizzes around ahead of you or it lags way behind you. However, and that's north and south. However, when you go kind of, I'm actually pointing east, when you fly east or west, it's not bad actually. It's pretty good because
It's not having to adjust for the magnetic.
yes, it's already leaning one way, for instance, and therefore when we turn, it's already kind of there. So it doesn't have that tendency to swing down too much. But the moment you turn off of east and west, it all starts to occur. And in the northern hemisphere, there's various ways of teaching this, but I got taught NUNOS. So it's another acronym or mnemonic that when you're in the northern hemisphere, if you're using the compass, you undershoot north and you overshoot south to allow for this. So what does that mean? Well, it means when you're on north of the equator, undershoot north. So there we are, we're turning from east onto north. What does the compass say?
It already wants to turn.
It's further around than me, sort of thing. So it's kind of almost ahead of me, but on the display it shows I'm still not on north yet. And as I come round onto north, it says I'm still not on north yet. But I've got, it maybe says I've got another 20 odd degrees to go. Depends on how much you bank and all sorts of things. But it's still got about 20 degrees. You know what? I'm going to roll out now. I'm going to undershoot north. As I roll out, the compass swings round, and with a bit of luck, it's about right. Undershoot north.
So what was fine.
So it works both ways. If you go from west onto north, you undershoot the number on the compass by say 20 degrees ish. East to north, same thing. So therefore, what about if you're going to go from east to south? You overshoot it. Because as we go around from east, 90, 100, 110, 120, 130, the compass suddenly races round sometimes, doesn't it? And says you're now at 200 degrees. You're like, oh my God, I'm already there, but you're not. You want to go past. So the compass is now saying, for instance, 200, 210, 220. And as you roll out again, depends on how much you banked and a few other factors, suddenly it swings back again and settles down, doesn't it? So you need to overshoot the heading onto south. By how much? It's a bit of guesswork sometimes almost. But at least it gets you in the ballpark. What's the other easy way to do it?
Probably DI.
But yeah, that's why we have it. It's not on my list, but that's why we have a DI. I don't want to get too much into aircraft general knowledge and instruments and all those sorts of things. But yeah, that's right. That's why we have a DI, because it's a lot more stable, but has no idea where north and south is. Well, the other method, like I said, I don't want to deviate too much off of this, is that, for instance, if you were heading east, well, nice and steady, your compass says that's south, just look out the window. There's a feature over there like Canary Wharf. Let's turn towards it. And then you can turn towards it. And then when you're there and steady, you can fine tune rather than just chasing a compass. So almost to a degree in a turn, you might as well not look at the compass, because it can literally, when we do steep turns, we've seen, haven't you? The thing does like this, spins around a couple of times. So we just get a sense of where the direction is, turn onto it and fine tune it afterwards. So the compass itself therefore suffers from magnetic dip, which causes problems when we are trying to turn. Sorry, if we pick on next sail change, when we're turning from a westerly or easterly direction to north and south, or when else does the compass sort of lie to us? Although you probably won't notice it. It's, for us, it's pretty slight. And the chances are you're not paying attention to it anyway when we. I could keep whispering it. He thinks I can't. He thinks I can't hear him.
You know the answer.
Shall I say it then?
Yeah,
Yeah, acceleration and deceleration.
exactly. See?
How did I know that?
And it's because that magnetic bar is dipping and it's almost slightly heavier one side than the other. So, of course, it's not even. Therefore, that heavier side will get subjected to accelerative and decelerative movements. If it was perfectly level, like at the equator, it pretty much doesn't happen, of course. This whole NUNOS or SONOS in the southern hemisphere at the equator pretty much does not happen at all. The same with the accelerative motions if you're perfectly on the equator or equally between the North and South Pole. But we're not. We're quite high up. How high up are we, Ross?
Oh, 50, approximately 50.
Yeah.
52. Oh, sorry.
Yeah. Look, best part of 52 degrees. So from the equator, we are over halfway up to the North Pole, aren't we?
Yeah.
Higher than people realise.
Higher because there's
How many miles from the North Pole are we? Correction, how many miles from the equator are we?
how many miles from the equator?
It's really easy to work out, isn't it? Because
If we're 52,
multiply that by,
60,
and therefore you have,
3,120.
yeah, give or take a touch because we're not quite 52, but yeah, exactly. Nautical miles from the equator. It's really, suddenly, you're doing amazing maths. It'd take me ages to measure that. But because the chart's already broken down into those increments, you can quite quickly do that sort of calculation. It's pretty cool.
I'm really impressed enough to do it then.
That's good. Yeah. There we are.
Yeah.
So it works. So from something, latitude and longitude that at first seems really cumbersome and awkward, and oh my God, it's as bad as feet and inches, isn't it? And all these other measurements and money, old money, etc. Latitude and longitude, almost when I first learned it seemed like that. It's like, oh God, how am I going to get my head around this? And slowly it started to make far more sense and became much easier to use. we go. Okay, so just to finish off that compass error, that acceleration, deceleration that alters the compass. For us, it's only slight because we just don't accelerate, decelerate that quickly. And also, chances are you're not looking at the compass during that either, so you just won't notice it. It's very, very slight. Cool. Any questions on that?
Yeah, just one. Can you remind me? So what about the Overshoot North and Undershoot South?
Yes. So in the northern hemisphere, so if you write in a column NU or above each other NUNOS, so write that vertically.
Yeah.
And the first N is northern. So in the northern hemisphere, you undershoot north and overshoot south.
Okay.
New north.
Cool. Perfect. Thank you.
But then in the southern hemisphere, it's the opposite way round. So you'd write sonus.
Yeah, we didn't do it this way, but yeah.
Yeah, I have heard of other kind of acronyms, mnemonics of it.
Yeah, we were using nippy on north and sluggish on south.
Yeah. Yeah, there we go.
But okay, cool. Thank you.
But it depends which hemisphere you're in, of course. Good. Okay. Right. Let's have a quick look. So, who wants to talk to me about time zones?
You mean local time zone or UTC time zone or?
Anything you like, Sophie.
There's
silence here.
Okay, so I'm in Montreal and it's 1:47 here. So why on earth you guys have a different time?
That's right. So what's, I mean, let's just, oops, I've just taken it off the screen, but let's just pretend for 1 second that really is the world. I mean, me sitting here, it's the same time no matter where I look at it. It's just right now. So why have time zones? It's all the same, Right now is the same as right now across the other side of the world. If I picked up my, Steffi's not there now, but if I picked up my phone and called somebody in Australia, I'm talking to them now, aren't I?
Yeah,
But they'd be
asleep.
Yeah, exactly. I'd have woken them up. So just state the obvious, obviously, Clue.
Basically, it's light and dark, isn't it? Because of the tilt of the Earth. And
yeah. It's just
we're all at the same time, but you'd be sleeping in daylight.
Yes, relatively speaking, it's just the same time all over. However, that just doesn't.
Midday, you
just
expect to see
exactly.
Right.
Yes, somewhere around there. Ross has nailed it on the head. At midday, you'd expect the sun to be pretty much the highest point in the sky, sort of thing, wouldn't you?
Yeah.
Roughly speaking, because it's not quite. But it's,
You
yeah.
want that wherever
And
you are in the
at
world.
night time, it should be dark, shouldn't it?
Yeah.
Not unless you live up in the north or south,
Oh,
and
yeah,
not maybe it's summer or winter. Yeah, that's right.
Daylight.
6 months of daylight. So that's one way of viewing it. We want it to be light during the daytime and dark at night time because that makes sense to us, doesn't it?
Yes.
Good. But somebody that's living in a room with no windows, it would be irrelevant, wouldn't it? Other than it'd really muck up their sleeping patterns if they weren't strict how they did it and tried to create a daytime and a nighttime. Okay, so time zones, yeah, it's we want to because the sun is only on one side, really, isn't it? As such, the Earth rotates and creates those days and nights. We want to try and split it down. So, is it even? How longitude is evenly spaced?
Mm-hmm.
Wouldn't it be easy if we just said, well, each longitude is a change in time by whatever it works out to?
That would make logical sense.
It would, wouldn't it?
Yeah.
So why don't they do that? Have you seen a time zone? See if you can grab one, James.
Let's see if I can find one.
Yeah, world time zones.
Yeah.
I do have one in Dropbox, but you should be able to Google it and get one up quite quickly. When you look at it on a map, they zigzag around all over the place.
Right.
Have you ever seen one?
No, but I can imagine.
International date zone.
Yeah.
Very
Yeah, exactly.
Because of trade.
Yeah, it wiggles around, doesn't it? It's all over the place.
Yeah. think it's to do with countries, isn't it?
Yes. So wouldn't it be so easy if they just divided it up by longitude and said each one? I was quickly trying to do the math whilst talking, but I'm not that good.
Bristol
Jeez.
would be now behind us, maybe. Or
If you divide 24 hours by 360, what do you get?
It was 25, wasn't it? 25 times.
I know, but if you did, we know 24 hours is in a day. That's how we measure it, isn't it? If you divide, who's got a calculator? Divide 24 by 360. Why doesn't it even work, does it? So if you got a calculator, oh, hang on, I can do it here.
0.063 occurring.
Good. So if I did 24 times 60, then equals, then divide that by 360. Each degree should be a 4-minute change in time. Yes, that would work. Yeah.
yeah.
Yeah, so each degree would just as a, oh God, where's everybody gone? There they are. Each degree about a 4-minute change in time. So you could then say like a 10 degree would be a 40-minute and so forth. So you could then find the 1 hour. Yeah, please, yeah, and that would work. But of course, at some point you've got to say which one day is the other.
Yeah.
When's the change from Monday to Tuesday? So you'd have to then just divide it by half the world. So you'd now be dividing 24. So quick think about this. You'd have to divide, because where's the start and where's the finish? Well, we're doing the prime meridian, but it doesn't suddenly go from day to night and all the rest of it. But it would work. Sorry, I'm waffling. Hey, there we are. James has got it. Oh, that's not the one I've seen, but it'll do nicely.
It does show the general.
Yes.
It's also on smart TV.
But they're not dead straight lines, are they? They shouldn't be. They wiggle around all over the place.
Okay, the way they've shown on this map is with like pluses and minuses
Yes.
and things all over the place.
Yeah, there we are. So yeah, you can see. So you can see I see it now. Yes. So on the what James is showing, +1 goes, for instance, halfway across Europe, but doesn't go anywhere near as far across Africa in North Africa anyway. But then southern or the middle of Africa, it's just as far as the Europe line, isn't it?
Yeah.
Look, there's the +1. It wiggles around. Look, all the way around this bit here. God, country days. What part of Africa it is?
There's bits like
Look at the +2.
America,
Suddenly
like
comes back around
-10,
here. Yeah.
-6 crossover, which is very odd.
Yeah. Look at the +6 in Asia.
Yeah.
The +5 goes way past it, doesn't it? Yeah. So the +6 is all on its own. In fact, apart from an island in the Indian Ocean, that's the only +6, isn't it? Just that splodge.
Yeah.
So you can't just simply say, if you travel 90 degree of arc on the Earth, the time has changed by this much. As far as local time or time zone is concerned, you'd have to know which country you're going to and what they apply. Because we have got that variation of at least an hour, for instance, in that example. In fact, if you go there, you could go +7, +5, +6, +5.5, all on the same longitude.
Yeah. Travel north for 2 hours and
you've gone back or gone forward in time just by going north or south, which doesn't make sense, does it? Because we normally assume you'd have to do east or west to change it.
Look at Anchorage, look at Alaska.
Yeah.
It's just all -9.
Yeah, it's all over the
Despite
place.
the fact that it almost extends to -12.
Yeah. Yeah, they don't want to be that far behind, do they?
No.
Look at that then, +14. What's that all about?
It was jarring when I was sailing across the Pacific. We had the boat clock, so we could keep sleeping with it because it was changing.
Look out in the Pacific Ocean, James. Never seen that before. It's +14 down there.
just juts out.
And what's that all about?
So I've crossed that.
How does that work?
Yeah, I didn't understand it either.
Well, you'd think so, wouldn't you? Anyway, I'm sure somebody will be able to tell me. Right, so there we are.
I think it's because it's the part where the international dateline sticks out, so they want to still be part of the same day.
Yes, I do believe that's right, yeah.
Yeah,
Just-
that's that little bit of the dateline.
Yeah, like
Yeah.
Tonga and that sort of area.
Okay, so you can see that it's not uniform. So you would have to know which country you're going to, which part of which country, as to exactly how much you're going to go forward or backwards according to the time zone, their local times, etc., isn't it?
Is that map going to UTC?
It's in comparison to, of course, Greenwich.
Greenwich.
Yay, the
GMT.
Greenwich Mean Time. Now, in aviation, we don't call it GMT, do we?
No.
We call it,
UTC.
which stands for
Universal Time Coordinate.
yeah, that's it. Universal Time Coordinated, or abbreviated, apart from UTC, as
Zulu.
Zulu, so a Z. Yay, well done, Sue, that's it. That's right. And we quite often say, we don't say UTC, we say Zulu. Good. Instead, when James show, can you see me? Not that it really matters.
I can stop sharing.
Yeah,
Can-
yeah, we can still see you, yeah.
Oh, really?
Oh, can you see what James is sharing at the same time?
Yes, we
Or
can.
Oh, cool. All right, that's right then. Because it looks weird. It looks funny on my phone, so I can flick between the two. Okay. That means I can't pull any funny faces in, right? I'm gonna watch us sit there, flick my nose. Right. Okay. So we all understand, yeah, somebody on the other side of the world is generally either 12 hours ahead or 12 hours behind, roughly speaking, isn't it? Just give or take a bit for now. Yes. But if relatively, we're all here at the same time, whether it be light or dark, whether your watch says differently when you look from space. But we're not in space, we're on the Earth's surface. So all based around GMT, or Universal Time Coordinated. You've got to either plus it or minus it, depending where you go. Now, we quite often do trips to France, which is how far ahead?
+1.
Yeah, just an hour ahead. Easy. Piece of cake, isn't it? You go there, you plus an hour, you come back, you minus an hour.
Depends on if we're on summertime or not.
Yeah, that's right. So now we're on summertime. So now you've got to do, if we depart here at 9 o'clock Zulu, it takes 2 hours to get there. What time locally are we there? And there's the problem. A simple sum like everybody's already going, oh, well done.
9 o'clock, so it's 10 o'clock, so 12.
Good day.
12 o'clock our time. It's 12, so 1 o'clock.
It's 1 o'clock. Look how long that took to work out.
Mm.
No, 1 o'clock their time, French time.
I need to write it down.
I know,
Yeah.
because you've got to allow for the journey, which was, I said 2 hours,
Plus the 1 hour that we're
Plus-
because of summertime.
plus the 1 hour
Plus the
ahead
1
that
hour
they are
ahead.
from that.
But why are you doing the 1 hour for our time if you're starting in Zulu time? You've already converted.
That's right. Or you could just jump to the 2 hours ahead.
Yeah, so you start 9.
So you do 9,
2 hours.
11 o'clock Zulu, and just add their 2 hours, which is 1 o'clock.
Oh, we're on summertime as well, aren't you?
Yeah.
Yeah.
Yeah, there you go.
It's a nightmare.
Summertime, they're the same.
Pardon?
In the summertime, aren't they the same?
No, they do a plus one as well.
So it's still an hour.
Yep, so they're still an hour ahead of us. I think I'm possibly wrong on this, but I got a sneaky feeling their French summertime starts at a slightly different time from us.
Yeah, about a week later.
It is,
Yeah.
isn't it? I think there's a slight cross. Is that right, Sophie?
Yes, it is.
Yes, I remembered something. Yeah, hey! I hope Catherine's on there listening.
And their summertime changes as well.
Yep.
Isn't it just 1 hour again?
On top of our 1 hour, which is on top of the 1 hour of UTC.
Yeah, we UTC +1 and then UTC +2. Yes.
Yeah. Now, without the travel, it's easy. Because if you said it's 9 o'clock UTC here, what time's it in France? You just add 2 hours, 11 o'clock. You've got to allow for the travel time, and that's where it gets complicated. So I certainly found it complicated. And then you've got to reverse it. Now, when we get into flight plans, we file all of those in Zulu. So you just work out it's +1, +2. You've got to allow for the travel. But like I say, as soon as you start throwing in the factor that you want to have lunch at 2 o'clock, well, what, 2 o'clock our time, 2 o'clock French time, 2 o'clock Zulu, and you're trying to juggle it backwards and forwards to work out what time to get there. Just gets a little, it takes a bit of practice.
Some European countries don't have a summertime, so it's exactly the same time now in Portugal as it is here.
Yeah.
They don't put their clocks forward.
Do they not?
Yeah,
Look.
for example, in Perth,
Oh,
the +8.
well, I'm just trying to think if they do fall in the same time zone. It would make sense because, of course, it comes back. Spain sort of starts to sit underneath us, doesn't it?
Yeah,
Portugal.
same time.
Yep, there we are.
Yeah.
So they're on the same time as us, but
Yes, Spain.
mainland Spain is an hour ahead. But
Same
Portugal's
time.
a bit further back, isn't it?
Portugal's slightly further
Yeah.
west.
Slightly further west, so it drops back into our time zone.
But then what about the Canary Islands? I suppose they're slightly further.
Yeah, they're ahead.
They are.
Yeah, they're classed as being they're classed as mainland Spain, even though they're slightly west.
Portugal.
Yes,
So technically they shouldn't be.
That's right.
Because they're further west of Portugal.
which is why you then get odd sunset and sunrise times.
Yes.
Oh yeah. But hopefully, suddenly the penny drops and it all starts to make a bit more sense.
But as you say, when you go on holiday, you're just there and you adjust.
That's right, you just
time and
adjust.
Forget about it.
Because you don't have to file flight plans and various other things and look at what time refueling is available and not available at airports and NOTAMs.
So mere mortals don't have to worry about it. Aviators
See, NOTAMs, what are they published in?
usually Zulu.
Zulu. So yes, you've got to start taking that into consideration as well.
Work out what it is.
Yeah, easy for us. It's just +1 for now, and then when wintertime comes, it's just what it is. So we got it quite easy compared to some countries, haven't we? To trying to win, but it's just what you're used to. But honestly, I tell you what, flight planning backwards and forwards does play with your mind a little bit.
If you look at flight radar and look at when a front flight was, sometimes it gives it into Zulu, sometimes
Yeah.
it works out. It looks like you landed before you landed.
Sorry, it's Malcolm talking. Good. Okay, so any questions about time zones? Loads, you say?
Yeah, I've got one now.
Yeah, go for it, Sophie.
Because each time I'm screwed. Why do we as like one country against another change time not at the same time? What the point? Why?
I have got no. It's going to be possibly astrological, isn't it? Political.
More political.
British summertime and stuff like that.
Yeah.
Let's do with your.
What about the farmers?
Yes.
It's all about attitudes, because that's what really affects the length.
Yeah,
of
that's right.
Yeah.
Yeah.
Because of course, for us, a certain wobble of the Earth, we have summertime. Yet Australia has wintertime. Because it's wobbled the other way, a bit further away from the sun, isn't it? There we are. But why would that change when a country decides it's it's summertime and not?
Well, if you're further up and the day gets longer, you get a more violent expansion, but also a worse contraction.
Otherwise, it's bound to be political, isn't it? So,
There's probably something
because
political.
I bet you can't just apply that logic to all the countries. I bet some have different reasons when it suddenly comes into summertime.
The sunsets are universal along a line of latitude. It will be the same local time, regardless where you are in the world.
Good. Let's have a quick look. What I've done that long time. I've got my notes. Compass. Oh yes, units of distance, because we did talk about latitude and longitude, which to a degree is a unit of distance in some respects, isn't it? Especially if we go around the equator, or we go from north to south. These big circles, do we call them big circles?
Great.
Yeah, we call them great circles. That's right, because they're the greatest they could be. Circumference, aren't they? Yes. Well, they go, that's right, through the centre of the Earth from north to south, don't they? And only one horizontally through the equator. Good. Yeah, they're the furthest distance round, aren't they? Okay, so what other units of distance do we have in aviation?
Meters.
Yep.
Height.
Yep, meters.
Feet.
Feet. Distance, just units of distance for a minute.
So you have statute miles and nautical miles.
Do we use statute miles in aviation?
No.
No, we definitely use nautical miles. definitely. Kilometers we use. So we've got, we said meters, feet, nautical miles, kilometers. Anything else? I mean, that's enough already.
Yeah.
There's possibly sort of one other, maybe, but it's not kind. But you could argue flight levels, for instance, but it's more or less the same thing as feet in some respects, isn't it?
Yeah.
Just multiplying it by thousands instead, isn't it? Okay. So okay, let's make life easy, because we're the ones that are sitting around deciding how the units of distance are going to work in aviation. I know. Why don't we say vertical is feet or imperial and horizontal is metric? I don't know why you'd do that, but let's do it for the fun of it. So we'll say if you're going to go up and down, you're going to measure it in feet. If you go horizontal, we'll do meters, kilometers. Yeah.
Depends if you're seeing something or if you're going somewhere.
Oh, hold on a minute. There's always one, isn't it? Right. So somebody else wants to put a little, a little caveat in there, So we've got rule number one. Rule number one, vertical is feet.
Yeah.
Yeah, feet and inches if you want. Feet, inches, we can even do miles if you really, really wanted to, but just feet and inches or feet. Horizontal, metric. Imperial up, metric, horizontal. There's rules 1 and 2, done. But somebody wants to put a bloody another rule in there, a little subcategory, or whatever you like to call it, don't they? People say, yeah, but hang on, let's have horizontal. What did you say?
If you're seeing, if it's about visibility, we do meters. But if it's about distance travelled or distance to travel or distance between a point, it's nautical miles.
But hang on, I thought we were doing metric horizontal, but you want to chuck another unit, nautical miles, in there now.
Not me personally.
Nautical miles isn't even kind of feet and inches, is it?
Well, a nautical miles, of course, predates meters, presumably.
Why don't we just do everything in nautical miles, vertical as well?
So you don't get confused. I know it's
where is it?
Oh, hold on. There's another one piping up now. Look. Right. Ah, yeah.
Everything should be feet. Everything is feet.
All right. Okay. So I'll tell you what then. So to keep James happy, if we're looking with our eyes, we'll say in meters. Happy with that? Visibility. Visibility.
If you're not going to go there, you're just going to look at it, and it can be meters.
So if we're going to measure something visibly, we're going to say meters, yeah? Should we go along with that, i.e. kilometers, for instance, yeah?
Mm-hmm.
Right, good. That keeps them.
Ask Jem why in my radio I say I'm 2 nautical miles away from the field or something like that, and not 2 kilometers or not 2 meters. Whereas I mean, I see the field.
It's about visibility.
Well, yeah, you see.
Yeah, well, I see it.
I'm sorry, we've written the rules now. We've just said horizontal visibly is metric.
2 kilometers away, but I don't know how far. Yeah.
Got it? But if we're going to measure something on the chart, we're going to say it's nautical miles.
Yes.
Why? Just because.
Because.
Why not? Well, because the chart is kind of done in nautical miles, because we just decided earlier on that it's all divided up by 360 degrees, minutes and seconds. Yeah, etc., etc. So let's not confuse it any further. So if we measure something on the chart, we better say we'll just stick to nautical miles, yeah? But if you look, we're going to say it's meters. All right? So the town is 2 nautical miles away that I can see at, whatever it is, kilometers. Yeah. That's right. Just to really, got to keep James happy, haven't we? Got to keep whoever it was that said we're going to stick to nautical miles across the chart. That was me. I'm saying that. So I'm putting my stamp on it. What else we got? Oh, but we did say vertically is feet, didn't we?
Yeah.
Yeah, fine. Are we going to stick to that?
Absolutely.
Yeah, of course. Unless.
I don't like unless.
Unless.
It can be converted to feet.
Well, why don't we just chuck a rule in there? Because we like to make things complicated. What about a clearance around a gathering of people?
Yeah.
Yeah.
Okay.
Why don't we say, just for fun, we'll call that meters?
As a distance.
Like 1,000 meters?
Yeah.
Just to chuck it in there. So we'll play the same logic to I know. Let's do a low. Let's create a low flying rule. Yeah, and we're going to say that as long as you keep 500 somethings away from, let's just say, any person, vehicle, vessel, or structure, you're not breaking the low flying rule. But it's a bubble, so we'll just call that feet.
500 feet.
And this is the problem we have, isn't it? There's no completely set fast rule as to horizontal is metric and vertical is imperial. It just doesn't quite work like that. Why? I'm not entirely sure. I'll be completely honest, but I get the chart. Nautical miles. There's no point in turning that into kilometers because that's done. It's nautical miles, isn't it? There's no point altering that.
It's like when you're
So why on earth do we say visibility is metric? Why don't we just measure it in nautical miles? I can see 3 nautical miles.
Do people understand how far a nautical mile is?
Yeah.
A metre is something that we use.
They were using nautical miles before.
Well, it depends how old you are. Doesn't it? Depends what you.
52 meters away, would you?
Depends what you've been learning, isn't it?
You'd say.
Now there is going to be somewhere along the line. So if anybody wants some homework, there's probably going to be a perfectly reasonable explanation behind all this. I can't quite see it. No. But anyway, that's how it is, isn't it?
It's probably differentiating it on reports or something.
I should think it's probably along those lines. Like
Boring,
was it you that said so, or somebody said just what we're more familiar with? Maybe it could even be as simple as that, couldn't it? But I mean, we're still road signs. Distance are in miles. They're not in meters, are they?
No.
The speedo in your car says it in miles per hour.
Sometimes.
Exactly. Yeah, that's right. It's sometimes kilometers as well, of course. So you can see it does. It's just not one unit fits all, is there? Okay, and then it does the whole horizontal in meters and height in feet does still work when you talk about clearances from buildings and clouds and those sorts of things as well at other times. But we do have these bubbles of sometimes they're just, for instance, a 500-foot bubble, whether it be horizontal or vertical, or a combo between an angle or 500-foot angle away from something. It's just 500 foot, for instance. And then you get the 1,000-foot rule, don't you? Same sort of deal. That's 1,000 foot above the highest fixed object. It's not 1,000 foot horizontally from it. It's just above it. And how many meters horizontally?
600.
Yeah, good. 600 meters. So it works okay there. We're in imperial vertical, metric horizontal. Yeah. But I still don't understand why you couldn't just leave it all in feet or just leave it all in meters. Maybe one day.
Take it all. None of our stuff is stationary, is it? So we're measuring it in knots per hour. So
yes, that's right. And this is why I said the chart at the end of the day is nautical miles, because that's been around for a long time. And of course, the aircraft are in knots, nautical miles now, because we're working on a nautical chart, as it were, or an aeronautical chart. So that kind of all makes sense. Get that? We know if you fly at 60 nautical miles an hour, give or take the slightly greater distance you're traveling because of your distance from Earth, but it's so insignificant. 60 nautical mile an hour, 1 hour, you're done 1 degree. It matches up with the chart then, as long as you're going vertical, not horizontal, unless you're at the equator. Oh, God. But it's the problems with flattening a sphere. It just goes back to where we started, isn't it? How do you flatten a sphere? Okay. So I'm not going to go right all the way through it, but, units of distance or the units we use, of course, it doesn't just end there. We get into measurements of volume. We could be using litres. We could be using US gallons. We could potentially be using imperial gallons, isn't there? But don't worry, then we also look at weights of fuel as well. Pounds, kilos. Yeah, quarts of oil. So yeah, there's many different units we have to deal with. And yes, in an ideal world, you can convert between them all. That's not easy. There are some conversion figures you might be able to remember. Some that don't matter unless you look them up.
It's basically ATPRs.
Yep.
Those conversions.
That's it, all those conversions. Okay, so any questions with sort of units of distance? I hope we've made that clear as mud. All right. So next on my list was the choice of chart. But what do I mean by the choice of chart.
Scale.
Yeah, the scale, the area you're actually covering.
Yeah.
Ideally, the same one you want to fly in. It's probably a good idea, isn't it?
The most up to date.
Yes, good. That's about updating charts, isn't it? So what determines the scale of the chart, Tony? Why would you choose a 1/4 mil, for instance? Or would you choose a 1/4 mil?
We probably would because of the speed that we're flying compared to a fast jet, or they're going over land a lot faster than
Yes,
us, so they don't need to
absolutely.
so much detail.
Yeah, you imagine, for example, navigating in a Dreamliner at 42,000 feet, doing close to the speed of sound on 1/4 mil charts. You're going to need a chart
A lot of charts.
every few minutes, aren't you? You're going to
One
be,
away.
that's one, that one's good, that one's good. You can fill the cockpit up with charts, absolutely. So it'd be crazy, wouldn't it, to try and use a 1/4 mil chart? You'd probably want a 1 mil or even a 2 mil chart or something. But that's whilst you're up high and fast. And you said, of course, like Malcolm, the distance you're traveling or the speed you're traveling, you might want to start to change that scale right down to what do we use, for instance, when we're trying to find a confined area. The old method, not the get the iPad out, but the old method.
1 in 50,000.
Yes, it is. And so, what does that mean? 1 in 50,000.
A lot more detail.
It-
OS.
But what does 1 in 50,000 actually mean? Just in case anybody isn't sure.
Oh, it's 1 unit, 50,000 centimeters.
Good. So 1 centimeter on the chart is 50,000 outside, isn't it? Excellent. And on this chart, 1 centimeter is
250,000.
outside. Excellent. So whatever you're measuring here, you just multiply it 250,000 times, and you'll get the distance outside, won't you, in the real world? Excellent. So good. That's the scale. So yes, if we are trying to just find a particular place, we want to navigate from Elstree, and we just want to go maybe up this way somewhere, and there's a house there we want to try and land at. Well, this chart would be absolutely perfect for navigating that route because we can see all the controlled airspace. But when we get there, well, the house isn't on this chart. And you have to kind of imagine, maybe you've never been there before. Somebody's described it. Yeah, you get the A to Z out, which is basically the same thing, isn't it? That's it. So you get your OS chart because it shows a lot more detail for that because it's blown up 5 times, and you can find the actual property, the field, with even the trees and the roads and the little pond near it and those sorts of things. And so that is how we used to do it. If you were going to go from, for instance, Southend right the way across to Bristol, you could use this 1/4 mil chart. It'd be okay, but that's by the time you fold, that's quite a big chart. And if you decided you were going to fly quite high, if you were allowed to maybe fly up at 5,000 feet, probably you don't need all this detail anymore. We'd go to a 1/2 mil chart. So if I just quickly, without making everybody see, if I run through to the other room, I think there's one upstairs on the wall, isn't it? What did we take to room? Yes, there we go. So it's an old one. We can see the scale on there is 1 in 500,000, and that same distance on the table now is only, in my hand, sort of 1, 2, not even 3 hands of finger of thumb across. So I haven't got to have quite such a big chart folded in the cockpit, but it doesn't show me the detail that the other chart did. But if I'm flying high, it doesn't matter. But if I'm going to start to descend down below, say, 5,000 feet, I'll need to go back onto that 1/4 mil chart. And as we arrive close to the private site, within 5 miles of it, we drop down into an OS chart. Hey, presto. Or you just use the iPad. So that's how we would do it. So there we are. Choice of chart is obviously the area, and depending on potentially how fast or how high you're going to fly. And
that's what my initial thoughts was to do with height. We're pretty much going to be below the transition layer, so we'd want to look for obstacles.
Yes, good. That's right. As soon as you're going up,
I didn't think distance initially.
Yeah, as soon as you're going up higher or faster, then suddenly the 1/4 mil chart is it's too much. You don't need it all. So you'll go into a 1/2 mil, and then you can even see, for instance, the one up on the wall over there. is, I think there might be 2 million. Got a sneaky feeling it might be 2 million or thereabouts. It's certainly about 1 to 2 mil. But with no good for doing a qualifying cross country on. Good. So any thoughts on choice of chart?
The only I'm confused about is Ordnance Survey doesn't do latitude and longitude.
No, it doesn't. Good.
So I get that it tells you
Yes.
where that house is, but how do you compute that with where you're at?
So why is an ordnance survey map basically metric and is squares, isn't it?
Yeah.
And they're
And
numbered
it's
and
A's and
you
noughts,
then
yeah.
divided into 10. So 3, 6 point whatever, and then they have a different numbering system though.
Yes, they do. And then there's areas as well. So they then put 2 letters on an area because if you can't divide. Think of the number of squares. If you divided the entire world by 1 kilometer squares, sure, yeah, 1 kilometer squares. If you divide the world by 1 kilometer squares, that's an awful lot of squares, isn't it? And that would make some ridiculously big numbers if you tried to do some sort of horizontal vertical reference to it. You'd be talking in the millions, wouldn't you? I mean, that's a lot of writing.
That's the genius of what 3 words.
That's right, exactly. Yeah, it's incredible, isn't it? What 3 words? It's not in aviation, kind of, but it's close.
You must have an accurate position.
Yeah, I do. Emergency services, I think, start to use it, don't they? Yeah.
Exactly to within what? How many meters?
Oh, it's tiny. It's like
3 meters square.
Yeah, it's tiny.
Might even be 1 meter square.
I think you're right. I think it's 3 meters, but it's small.
Yeah.
Very, very small.
You could know.
Oh God!
The counter.
Between the front door and the back door. Yeah, that's right.
James is state.
Like parcel delivery.
In Scotland.
Anyway, yes. So yes, the OS grid reference is then broken down. Usually it's got a couple of letters in front of it to designate an area, and then you can chop it back down into I'm sure it is 999 by 999, isn't it? That makes sense. I'm sure it is off the top of my head. So you could do horizontally all the 9s, 999, and vertically 999. And then you'd have to change the area. Yeah, I'm sure it is, isn't it? Because it's 6 figure. I'm sure it goes up to 9s. I'd have to look on that. Double check on that. Because we have certain ones we use all the time. Okay. Right. I just wanted to talk a little bit about dead reckoning. So we've looked at the form of the Earth and the problems with trying to flatten a sphere to create a chart. But in certain ways, I haven't gone into how they project it, one thing or another, but they can minimize the distortion to a degree that's acceptable, that sort of averages it out, makes it usable, especially for what we're doing. And then, of course, we decided we want to go from A to B, maybe with a point in the middle, a turn here and there. And we can work out on a chart what that direction is, that track via North Pole, South Pole. But then we've got to apply a bit of error for the compass because that's what we're actually going to use when we're in the air, isn't it? So what else have we got to calculate for? We've drawn the black line. We could do this, I suppose, couldn't we? But we've drawn a black line on the chart. We've used a protractor to measure the angle. We could just simply say going from east to west is 270 degrees.
Yeah.
Brilliant. So we've worked out 270 degrees. If we were to skip to the straight away to the compass part, let's just say the compass had an error of a couple of degrees. We'd have to work out which way it is, wouldn't we? Yeah. And then plus or minus it. That's fairly easy to do. For us at the moment, it's pretty much nothing. Yeah. So there's nothing to be done there. What else we've got to calculate for or allow for? The wind. Good. So we've got to find out what the wind is, what the surface wind.
What wind at the height we want to fly at.
Good. Because, of course, everybody always jumps to the 2,000 foot wind, but that's only if you're flying at 2,000 feet. What about if you've got different planned legs? What about if you're going over Wales and you've got to start climbing to get to the top of the mountains? You've got to use a different wind velocity, haven't you? And it's going to be different across the other side of the country anyway. And I think that does get forgotten sometimes. Everybody just jumps on it and says, oh, well, the wind today is 360 degrees at 10 knots because that box says so. But what about the other boxes where you're traveling? What about the fact you're not at 2,000 feet? We're planning to do this one at 4,000 feet. So don't forget about that, because it could be significant, the difference. Might be minor, but it could be significant. And then we've got to apply that. So if we said we're going to go from east to west with a northerly wind at 2,000 feet, what's that going to do to your track?
You'll push us left.
It is. That's right. So it's going to reduce the track, isn't it? So you might still be heading 270 degrees, but you're drifting off to the left. So you're actually tracking, let's just say 260. Yeah. So therefore, what do?
Make a correction.
You do to the right. Simple, isn't it?
No.
What's this?
How far off you
Yeah.
drifted to know?
Well, there is that. Yeah, that's something else, isn't it? So this is the whole planning it out beforehand. We're pre-planning it, aren't we? We're sort of nudging towards.
Think of this on the fly, as it were.
That's what you.
But but this is a good skill to have. Yes.
To work out.
This is where we're going with this, right?
That's right. Yeah. See, it's not just a random conversation.
This is where it comes in. What match you can do.
Yeah. See, yes, of course, I could ask you to get your whiz wheels out. We could just skip the whiz wheel and go straight into some software application, whether it be Sky Demon or E6B or. I can skip all of that, but I tell you what, that ability just to do what we've just done there whilst flying is invaluable, because what if you get up in the air and you suddenly realise you've made a complete muck up of it and you calculated all the wrong headings because you thought the wind was the other way?
You've got to work out the track to get back on course.
Yes. But wouldn't it be easy if you could just do a quick mental calculation? Oh my gosh, I've done it completely wrong. I'm heading west. The wind's coming from the north. I'm going to drift off to the left, i.e. a lower number. So I need to apply a correction, positive correction, to get to stay on my 270. It means my helicopter is going to be pointing slightly off to the right compared to what I think it should be. Job's the good one. Hey, you're already halfway winning the battle now from the errors we made on the ground. The trick, or the real skill, is working out exactly how much to correct, and then also what else will be affected.
Travel time?
Because
Because you're not going in a straight line all of a sudden. You're up at an angle.
oh no, yeah, you could be in a straight line, as in you're still tracking east to west, but you're
Speed.
yeah, go on. Anybody online? Yeah, everybody's very quiet online. Yeah, please go for it. Oops, I can't see you.
It's going to affect your speed depending on the wind direction.
Yes, of course, yeah. Because I was just about to chuck in there, and you're just traveling at 60 nautical miles an hour. So how far were you going 1 hour? And somebody's going to go 60 miles. But what about the wind? If the wind is blowing at you, just playing devil's advocate, if the wind is blowing at you at 60 mile an hour, how far do you go in 1 hour? Nowhere. What about if it's behind you at 60 nautical miles an hour?
What's the line?
You do 120 miles, don't you? Brilliant. Okay. So, of course, any change in heading compared to the original heading is going to affect, even if it's a tiny bit, it's going to affect the timing because of your ground speed. So, like I said, this is where the real kind of picked on Ross again, I'm afraid. This is where the real skill comes into it. You know, and even after years of practice, you still can't. It's not perfect, but you start to get a bit of a feel for. Well, I'm traveling this way at this airspeed, which is use easy numbers for a minute, 60 nautical mile an hour. The wind is coming at me from the north by 20 knots. I'm going to drift to the left by. Anybody want to have a guess?
No, someone else.
You said the numbers again?
60 nautical mile at airspeed. The wind's coming from my right, 90 degrees to my right at 20 knots. What's it going to do, first of all, to how much drift? But just have a guess.
45.
Blimey, that's a bit much. So, oh, pretty good. Malcolm. Hey, Malcolm's gone for 18. James is going to say
20. I liked 18, but I said 20.
so who's got a whiz wheel to hand? Anybody got a whiz wheel? You got one in there? Oh, I can see it sticking out. Tony at the end. The whiz wheel, that is. Ross?
I was going to go with like 20.
20 degree. So apart from Tony's 45, you're all kind of from 20 degree to Malcolm said 18. Oh, there we are. Sue said 15. Yeah, 20 knot crosswind, but you're doing 60 nautical miles an hour. So Tony's quickly working it out. Let's have a look over his shoulder.
Was it north wind?
So yeah, you're doing 60 nautical miles an hour. So he's going to put his little blue dot at 60. That's it. The wind's coming from the north. If you've got a little, do you want a board marker, Tony?
Oh yeah.
Yeah, I'll stop that a second. So I just don't make everybody see. So I'm going to run around my phone.
Cheers.
Oh. So I said, I don't know how much you'll see of Tony's CRP, but he's going to now mark downwards to 40 because, of course, if you flew into the wind, it would slow you down to 40 knot ground speed. And I said you're going to travel west. And what have you got for now without any jiggling?
18. 18.
Yeah, somewhere between 18 and 20. But the point is,
You need to do his wiggle wiggle though.
pretty damn close. That's right, because unfortunately, that doesn't completely resolve it because you're experiencing 18 degree of drift. So you've got to therefore turn to the right by 18. That's it. So 288. And it's actually pushed that drift a tiny bit further, 20 degrees. So just jiggle a little bit more to 290 and it'll probably resolve it. 20 degree. There we are. And what did James say?
I did say 20, but I like that.
Hey!
I like Malcolm's 18.
That's right. Yeah. But we managed to come to those numbers just in our heads by just thinking about it. But what will be interesting, Tony, is actually I'm going to fly a bit. Tony, don't put that away a second. Let's fly a bit faster. Let's do 120. How much drift do you get then? You don't need to change anything. You just need to move that slider down.
10.
Surely it'd be half.
You think?
No, even less.
How much drift, Tony?
110.
120.
120.
Yep.
Okay.
Heading west.
I don't think it's that simple.
No.
270.
They're a little bit resolving because it's 10 degrees. Yeah,
It's probably some sort of percentage.
But it will be pretty damn close.
Yeah.
It's halved it.
How's that?
Yeah.
Genuinely after. I don't think it was that simple.
So you can see that flying at the same heading of 270 degrees, the faster you fly, the less effect the wind has on drift, doesn't it?
Yeah, because you're going through it quicker.
Because you're making greater progress comparative. We just increased our airspeed by 100%, but the wind hasn't changed. It's still the same percentage, wasn't it? It hasn't altered. So naturally, we're going to take further steps forward than we are going to get blown sideways. But if we slowed right down to,
30.
let's slow down to 0 knots. How much drift do we get then? You're going to get 90 degree of drift, aren't you? You're going to go sideways.
Just do directly south.
Yes. So we can start to get a feel for it. And that's it. The tricky bit then is also the ground speed gets affected, doesn't it? Because when you travel west with that northerly wind, and I said a 90 degree wind to the right, you think, well, the wind's neither in front nor behind. However, when you look at it on the whiz wheel, it does create a very slight headwind element by the time you compensate if you're slightly towards the wind, and it creates a little bit of a headwind component. So it does just bring your ground speed down a tiny bit.
Right.
Only tiny bit. Yeah. So without even, okay, we have now looked at Tony's whiz wheel, but without even looking at it, we can see that if we've completely mucked up and forgot to bring our needle with all our calculations on it, there's a chance with a bit of practice. I want to head west. I'm doing 60 nautical mile an hour. The wind's from the right at 20 knots. I'm going to get about 20 degree of drift. I better turn to the right by 20, and it's going to slow me down a bit. Therefore, I won't be doing a mile a minute. I'll be doing a little bit less. And that'll be close enough for the speeds we fly at for now to get you there. If I fly directly into the wind, it's easy, no drift, but the ground speed will reduce to 40 knots. And if I turn around and go the other way, no drift, but I'll be doing 80 knots. So north, I'll be doing less than a mile a minute, and south, I'll be doing more than a mile a minute. It's close enough to kind of roughly do it. But of course, we know that with whiz wheel, etc., we can really fine tune it. But only as good as,
Person putting the information in.
or, well, yeah, at both ends, i.e. the 214.
And yeah,
Relying on the forecast. Is it really doing that up there?
Has it changed in that?
Yes.
How you've been flying? Yeah. Just when you thought you got it sussed wrong.
Yeah.
Yeah.
Or you used Skydim and that you shows you. But
Yeah, that's right. To be fair, nowadays with a lot of the applications we've got and the accuracies of 214s, unless there's a really complex weather system around, they're normally pretty damn good. But sometimes, yeah, you get up there and you instantly get a feel for it. This is I've compensated too much. I can feel it, I can see it. Literally, I'm going off over there somewhere. I'm not going where I should be going. And you quickly make I don't know, maybe a 10 degree I've overcompensated. I'll just come back 10 degrees. Poor Rosler, he's like, oh God. But you start to get a feel for it in time.
Yeah.
Yep.
Oh, good.
Does start to make a bit of sense. And then just want to finish off on radio navigation. So what is radio navigation? So you go on the radio and say, help, I need help with navigation. That's not quite it, but
So you've got the omnidirectional.
oh, very good, Sue. Yes, could be. Yeah.
That's it, yes.
That's right. That's right. So there's stations on the ground, transmitters that transmit signals in all directions, but the signals just varied slightly depending on the direction it's transmitted. And therefore, if we have a bit of equipment in the aircraft that can detect those variations, it can maybe put it onto a scale of some description that makes sense to us, perhaps with angles, degrees, those sorts of things. And that's more or less describing what the VOR station does on the ground and what our VOR in the cockpit instrument does, more or less. So well, that's that done. Yes, now not, if we just stick to VORs, because there are others. Yeah, so the DME is if you've got distance measuring equipment. So this same, potentially maybe this VOR that you've got in the cockpit or something attached to it can not only detect the angle of the signal, but maybe how far away the signal is, the distance. And we can put it up as, a figure for us so we know how far away the signal is. And that can be really useful because if you know the angle you are from a signal and you know how far you are from a signal, you can literally find out where you're on a map. Pretty cool, huh?
Allegedly. I can see that.
Yeah. Therefore, does it tell you what direction? Therefore, does it tell you what direction you're flying in?
If you did two of them, it would.
Yes.
260, the 2.5. Yeah.
Or if you took a measurement of one moment in time and then another measurement at another moment in time, you can see exactly that's it. You can see you've gone from A to B, and you can work out your distance. So something that a VOR doesn't tell you is the direction you're flying in.
Yeah.
Only tells you where you are in relation to a bearing, either to or from that signal, but it's really from that signal. Does that make sense?
Yeah.
So do we see VORs on our charts?
Yes.
Good, we do. But if you've actually got that piece of equipment in the helicopter, now to be fair, not many helicopters have them in nowadays. But yeah, we're quite spoiled. We've got a few around here. So there's us at Elstree. We've got one really close to us, Bovington. We've got another one that's not very far away, Brooklands Park. We've got Bark Bay VOR. That's right. We've got the Compton VOR. We've got one down at Biggin Hill as well. We're literally surrounded by them. You go further up north and they become a bit few and far between. I can't remember how many are left in the country now. I think last time it was 32.
Another one down here somewhere as well. Midhurst.
Yeah. So there's quite a few. You start seeing them. Look, there's around the end, Seaford. Yeah.
Oh, there you go. There's one. I've never seen this before.
Yeah, there's quite a few around, but they're slowly going out of operation, aren't they? Because they have a life expectancy of X amount of years before they have to have a major overhaul or whatever, and it must be very costly. And they're sort of slowly being turned off,
And I suppose
slowly.
the argument then is because there's all the sat navs and
Yes,
other things, we don't necessarily need
yes,
sort of sat
Which they
navs.
get an ad when I was coming back from.
that's right. Go wind back the clock a number of years. They were flying with no GPS whatsoever because it wasn't really around at that point in time. You were maybe at war, so you've got no lights on, you're in the dark, there's no lights on the ground, so you can't really identify ground features very easily. In fact, you might even be above the cloud. That's right. How the heck do you navigate? Well, you do a bit of dead reckoning first, don't you? Because you know where you've taken off from. And if you've got some sort of half decent forecast on the upper wind, I don't know how they did it back then. I think they sent balloons up, didn't they? And watched how far they travelled and stuff like that. A bit like chucking a thingy in the water, wasn't it? Count how many knots go past in there we are. There's nautical miles an hour.
It used to be knots in a rope.
Yeah, that's right.
It was first developed.
Yep, chucked into the water. Yeah.
And you dragged it by the boat at that time.
Yeah, that's it.
Explains why it's not.
Well, no, the division came up first, and then you tie the knots in the right place to work out. Yes. So you would. What about if you use a radio signal that doesn't matter if it's cloudy because it, for the most part, gets through it, doesn't it? Line of sight, so it's fairly straight. So if you could transmit a signal, and if you had something to receive it, and if that something that received it could maybe point towards the signal, that'd be amazing because at least you know where the signal is. If you make sure that signal's transmitted near to where you want to be landing, at least you can fly to the signal and then maybe get low enough to see where you're actually going and find the airfield.
Unless there's a storm.
Unless there's a storm, because it happens to interfere. So what I've just been describing is something you're unlikely to ever come across. So it is actually one of them in the jet range, but an NDB. But it's a non-directional beacon. Yeah, so the instrument in there, a little needle, can only point towards the signal. It can't tell you what radio you're on from the signal. So it has no idea what actual bearing it is. It just points. But you could literally turn the aircraft towards it and fly towards that signal. So tuning it on the radio, and away you go. But yeah, they had problems, accuracies, how far away you are. Storms played havoc with the needles and the signals and all sorts of things. There's a myriad of different things. They're not amazing. But back in the day, I mean, there must have been a lifesaver.
Yeah.
Then you kind of, I think, VORs obviously then came around, so they certainly went before NDBs. So they could then modulate the signal and you could actually work out exactly what angle you are from it. Brilliant, even better. And in fact, if you have two of these VORs, you say you can triangulate them, as it were, get two position fixes. And we're kind of loosely nudging towards GPS stuff now, aren't we? But I tell you, I'll tell you what, rather than have these radio signals on the ground, let's chuck them up in the sky, up in space, and have lots of them transmitting all these different signals down with timestamps and God knows what else. And with 3/4 of those, you can do it all three-dimensionally, even better. And there we are. We've got onto GPS. Incidentally, do we as far as a study, a part of the syllabus, do we call it GPS or do we call it something else?
Something else.
It is. We call it GNSS, the Global Navigation Satellite System, that's made up of actually a few countries of satellites and things. So rather than just relying on one, they've made up of quite a few. They've all sort of clubbed together and said, okay, we'll all use one another's satellites. With a bit of luck, no matter where you are in the world, should a bit of luck be able to find where you are. Pretty cool. And it's very reliable now, isn't it? There was a time when they used to drop out and all sorts of things, but now, by God, it's incredibly reliable. Yeah, most navigation systems in big aircraft all entirely rely upon it, don't they? More or less. You have inertia ones as well and things, but it's mostly all born from the GNSS. Okay, so anyway, radio navigation. Yeah, we've got all these stations across the country that are sending out these signals that potentially you could use if you've got the equipment in the aircraft. So Tony, you fly the 44. How many VORs has that got in it?
None.
How many NDBs has it got in it?
None.
Oh, it's got some DME equipment, hasn't it?
No.
Ah. Sue, you fly the R22. How many VORs? And yeah. Ross, you fly the 22. James, you fly the Cadbury. What's it got in it?
Has got to be a lot.
Hey!
It does.
Yes. Yeah, so it has got a VR on it.
We'll just follow you then.
Yeah. You can argue the iPad has all of these things combined.
And if you don't, I don't want to put it down, but if you don't use the VR on a regular basis, how quick and easy is it to use?
Yeah, no, it's very easy to fall out of favour with them.
It is, isn't it?
Yeah.
Because very easily it reads backwards.
Yeah.
And it, as the left becomes right, right becomes left.
No, it's about that.
Yes.
Yeah.
You've got to be a little bit careful that the
Set on 2 or 3.
the signals on the chart, you've got to remember, all go outwards. Like it's always described as spokes of a wheel in the books, isn't it? You've got to remember it goes from there outwards. So if we took the BPK for a minute, you can see the arrow and it's magnetic. It's not true north, it's designed, but it's lined with. That one pointing out the top, what bearing would that be? Well, straight out the north top is north. 360, and we call that the 360 radial. Yeah. Great. So if we were over here, you would say we're sitting on the 360 radial. That makes sense, doesn't it?
Yeah.
Everybody with that?
Yeah.
If you were facing this way towards it, would you say you are flying?
Yeah.
You are, but you're on the 360 radial.
Yeah, you're not facing north, though, are you? You're facing south. Like the runway.
Yes, but strictly speaking, you're on the 360 radial. You're not on the 180. You might be facing, heading towards eventually as you cross over the 180, but you're still on the 360. Okay, so there's problem number one, as it were, that you're having to deal with when you're in the air. So you're on the 360 radial. If you're north of it, you're on the 360 radial, aren't you? Good. So if you're facing it, are you flying to or from the 360 radial? Yes, because you're going towards the signal. Brilliant. Okay. If you had a little line in the cockpit that showed you the radial could be out to your right or it could be out to your left, if you were slightly off of it to one side, let's just say visually you're over here, you're slightly, as we see it, to the right of it, but you're flying down the page towards it, would that bar visually in the cockpit be out to the left or to the right?
Oh, God.
It'd be out to the right because it has no idea which way you're facing. It assumes you're facing away from it because you're going from the signal. So the course deviation indicator is out to the right. But when you turn around, it does that. The bar's still out to the right.
Yeah.
But it's not. It's out over there. It would be if you're this way around. This is correct. So it has no idea which way you're facing. And when you realise that it doesn't know which way you're facing, it starts to make a bit more sense.
No, you can set
Do you
it.
then use the compass as a secondary
You can
instrument
set it to be to or from.
help
You should
on
know.
that?
You shouldn't
If
be so
you're-
lost.
If you know you're on the
should know if you're
360
north or
radial,
east.
but you're going
Yeah.
south, the compass should say south.
Yeah, exactly.
Yeah.
Yeah, that's it. Yes, you can help use the compass just to help clear your mind as to, but then you've got to work out which way you need to turn to intercept that
Set it.
radial.
Got it.
And in this instant, it's actually, even though the course deviation indicates out to the right, because it's if you face this way, it's out to the right, like that, for instance, you've got to turn the other way.
All straightforward.
Not very straightforward. So when you're flying away, when you're flying from the signal, and you've got the, for instance, the 360 selected, it's all in the logical sense. If the CDI says it's out there, it is out there, and you just have to move off to the right, as it were, to intercept it. It's out to left, it's to the left. If we go the other way, we all know the trick is actually just to select the opposite radial And it's then makes sense. It's still in the logical sense. If the CDI is out to the right, yeah, go to the right. You intercept it that way by selecting the opposite radial.
Okay.
Yes. So it is one of those things that the VR, unless you use it on a regular basis, it could be easily catch you out in the air. However, at the end of the day, like James almost sort of intimated, if you just try it and see what happens, if you fly one way and it does the wrong thing, well, it must be the other way then. Just by the process of elimination, it's a 50-50, isn't it? You got half a chance of guessing it right. But you can work it out, obviously, like I say. But yeah, it's half the time. But then, of course, when you get onto a test, if you have a VOR on the aircraft, the examiner can ask it in several different ways, couldn't they? They could say, fly towards the 36 radial, want to intercept it. You could be north of it. Or they could say, fly towards the 180 radial, which is completely the other direction, south of it.
You don't have to worry about it.
Good.
Just to say that's the advantage if you got 22.
Yes. And if you got all the gear in the helicopter, of course, they can ask for any of it. They could ask for a sat nav, so a route direct or various other things, functions it can do, VOR, NDB.
An hour before getting
Yeah. So what we do is we get my label maker quick before you go out flying, just write INOP and stick it on it. Inoperable. Nope, that one doesn't work. Nope, that doesn't work. Oh, it looks all right to me. No, honestly, it doesn't work. Yeah, just pull the plug out on the back of it. Well, there we go. There's a little bit of just a smidgen of radio navigation. Any questions?
Did we actually cover, not that I particularly want to, that decimalisation?
Oh no, so we didn't.
Do you want to do it another night before our brains go?
Well, it's we literally don't use it. It's relatively easy, but could be very complicated. And we've fallen into this trap, haven't we, before? Because a question asked it in decimalisation. It took a moment to kind of finally work it out. So if you were to decimalize degrees, minutes, and seconds, what would 1 degree, 30 minutes, and 30 seconds be equivalent to?
That's 1.5.
Yeah. So in my head, it'd be 1.55.
Yeah.
Cool. That's it. So that's
30's half and
Yeah.
of course.
You can do the conversion with the calculator. Problem is if you don't know if they're decimal.
However, I don't think it is that. It'd be sure, isn't it written 1.0505?
As they're leaving it, they're putting the extra 0.
No, it would be. No, sorry, no, it'd be 1.5050, wouldn't it? Yeah, of course it would. Yeah, silly me. All right. So it'd be 1.5050 if that's how they're going to do it down to the tenths. Because it's half. Yeah. Because it'll be up to 100, which is where we found 1 degree 65. You think, well, you can't have 65 minutes. It'll be 160 becomes suddenly 2. You know, you can have 159 and then 160.
Computers preference.
Yeah, but because actually it's really easy. If we all used decimalized LAT and long, it's really simple because you just move the decimal point. Everything's divided by 100. Real simple, or 10. Yes, like our currency. Yeah, you know, there's 10 pennies in 10p. There's 10 10p's in a pound. There's 1 pounds in a tenner, and there's 10 of those in 100, and it goes on. It's so simple, isn't it? You just shift the decimal point around, and so therefore, LAT and long decimalized is relatively simple in comparison, rather than realizing there's 60 nautical miles at 60 mile an hour in 1 degree, or 60 minutes of travel in 1 degree, or 60 seconds in one of those minutes of what?
Yeah, I suppose so.
1 degree.
I think it's making it universal.
Yeah, it is.
It's when you've got 2 going between.
I say, wouldn't it be easy if everything was then just metric?
Yeah.
Horizontal distances, vertical distances, volumes, just be very simple. Maybe one day. Well, there we go. Oh, gone very quick. Is everybody still there online?
Yep.
Yeah, still here. Thank you.
I've lost 1 or 2.
Yeah.
I'm not surprised. Sorry, I've tried to make it as interesting as possible. and with their phones, etc. And Carl, I hope some of that helped with what you've already been doing, complemented what you've been learning.
Yeah, that
It's a, I mean, gosh, we've only just touched upon navigation in a 2-hour window. It's easily a 10-hour subject or more just by itself. Well, actually, to be honest, it's way more than that, because you keep learning, don't you? Over and over again. But
That's why
hopefully,
we're here.
hey, that's it. Well, hopefully, it's touched upon some areas that have cleared something up for people, and just giving you a bit of an overview of kind of where it all started from. We've gone back to looking at that globe with latitude and longitude, and how we managed to split it up and then flatten it out, and then start making some measurements, but realizing there's some distortions. So a straight line isn't a straight line unless you're going up or down. Yeah, this is it.